Well, hello, good people. Today we are talking about refraction and Snell's law. And I'm going to make this a little bit bigger here. And there's the bell. Class is ready to begin. Hey, here I have a little pencil and a beaker full of water. And if you look very closely, you'll notice a few different attributes about this pencil. First, you'll see that where it's in the water, it looks much bigger than it does when it's outside of the water. Let me see if I can make this even bigger here. Okay. You'll see that when it's in the water, it looks much bigger than it does when it's outside of the water. You can see that this image here is a little bit magnified. Also, you'll see here that if you look right at the water line there, can you see how right at the water line it kind of looks like the pencil is a little bit broken? This is kind of hard for me to show you because you are a video camera right now. Not you. You in real life are a real human being, and that is wonderful. But I'm trying to hold this up to a video camera. Hey, can you see how right at the water line there, it looks like this pencil is kind of split in two and a little bit disjointed. Again, very, very hard to show at the camera, but you could do this with your own pencil and your own cup of water at home. We see that there's a lot of things going on here. That this pencil is not actually where it really is in real life. Well, today we're going to talk about refraction of light and Snell's law, which is really just the law of refraction. We have learned already, sorry about my mouse, keep going over there. We have learned already thus far in this unit about lenses and mirrors, and we've learned all about how lenses work and how they refract light in different ways, and we've already done all that, but we never actually talked about, how does a lens actually refract light? We know that it does, and we know that it can refract light to create an image, but we never talked about, actually, how does that happen? Well, that's what we're addressing today, is how does refraction actually happen for light, and then what is Snell's law, what is the law of refraction, and how can we use it to help understand how refraction actually looks and what it looks like in real life. So, let's go ahead and get started. Okay, first I'm going to erase this pesky little annoying dot that I accidentally drew. Yay! Now we're going to talk about refraction. You will remember back in the day when we drew a little picture of a little road right here like this. And then, do you remember I had a little car going down the road and it was going this way? Those are the front two tires, and here are my back two tires. Here's my little car. I had a little car going down a road, and we said, hey, what if as this car was going down the road, then all of a sudden it ran into some bushes over here? And we said, what if the front tire ran off the road and ran into the bushes? Well, we said this car would take a little turn. I'll show you here on my whiteboard here because it's much easier to show when I can also point at what I'm drawing. Here we have, Here we have a road. And here I have my little car that is traveling along that road. Well, if one of the tires, if this bottom tire ends up, if one of these tires, if this bottom tire here ends up in the bushes, what happens is this bottom tire is going to slow down, but the top tire is going to keep going fast. So the top tire will go fast, the bottom tire will go slow, and this thing will turn. We said that's what refraction is. It's what happens when a wave encounters a new medium. The part of the wave that's still in the old medium, the slow medium, or the part of the wave that's still in the old medium, in this case the fast medium, that part of the wave will keep going fast. The part of the wave that's in the slower medium will slow down, and so the wave will turn as a result. We'll see that light does the same thing. That light will go, when it enters a new medium, it'll turn if part of the wavefront is in a slower medium and part of the wavefront is in a little bit of a faster medium. Now, here's the issue is you're saying, Miss Wilson, that all sounds good and fine, but last time we talked, you actually told me that light always travels the same speed, and that speed is c all the time. And you said all different types of light travel the same speed. Well, that is true. And it's also true that light slows down in a new medium. And you say, Ms. Wilson, how can both these things be true at the same time? Well, let me show you. Let's look at a picture of some light headed into some water. So here's some water right here. Here's some little water molecules that are hanging out in the water. And then let's draw a little light ray on its way in. Here's the little light ray on its way in. The little light ray, when it's on its way into the water, will be traveling at a speed c, because that's how fast little light rays travel. But then when it gets to this water molecule, it's going to spend some time hanging out here. In fact, it's going to get absorbed by the water molecule and then spit back out again and continue on its merry way. Now, students often ask, okay, Ms. Wilson, what do you mean it's going to get absorbed by the water molecule and then spit back out? Well, the truth is that Thank you, Belle. The truth is that really a little electron inside of that water molecule is going to jump up to the next little energy level, and then because it'll absorb the energy of the light, so the light ray will come in, the electron will absorb the energy of the light, it'll jump up to the next little energy level, and then that electron will hang out there for a while. When it drops back down, it'll release energy again, and it'll release energy in the form of a photon. So literally what happens is the atom absorbs the energy of the light and then spits it back out in the form of light again. So the light wave comes in, the atom absorbs the light for a second, and then spits it back out in the form of a photon. When this little photon gets spit back out, it travels at a speed c until it gets to the next little atom. When it gets to the next little atom, the atom absorbs the energy until it spits it back out again. When it spits it back out again, it travels at a speed c. Now here's the question is, how fast is the light traveling when it's absorbed by this little water molecule? And the correct answer is 0. It's not traveling. That energy has been absorbed by that little electron. And so the light is not traveling when it's at the atoms, it's only traveling between the atoms. It's kind of like a car that's going on a really long road trip. When the car's on the road, it's driving at 75 miles an hour the whole way down the road, but every once in a while the car has to veer off of the highway and take a little pit stop. When it veers off the highway, it takes a little pit stop, it stops at a little gas station, refills. Hey, when it's at the gas station, its speed is 0. When it's on the highway, its speed is 75. If you asked it, hey, how fast were you going on the highway when you were moving? The car would say, oh, I was going at 75 miles an hour. But then if you asked, but how fast was your trip overall? The car would say, well, I guess that on average, I must have gone less than 75 miles an hour because I was going mostly 75 miles an hour, but I have to account for my stopping time. Light is the same way. Light, when it's traveling, is always traveling at speed c, but sometimes it'll stop. And so the average speed of light is less in a medium where it has molecules to run into. The average speed of light is less because it's traveling c between the molecules and then it's not moving when it's being absorbed by a molecule. So you could see that sometimes light will travel faster or travel slower depending on its medium. Not because it's actually traveling faster or slower, but because the speed of the light when it's at one of those molecules is 0, so the average speed is less. There's a way to measure how fast or how slow a light goes when it's in a new medium. And the way that we measure that is we measure that with this value called n, where n stands for what we call the index of refraction. The index of refraction. The index of refraction is a ratio of speeds. The index of refraction is equal to c divided by v, where c is the speed of light in a vacuum. You already know that. It's 299792458 meters per second. And v is the speed of light in the medium. And when we say the speed of light in the medium, we really mean the average speed. The average speed of light in the medium. This equation tells you exactly how much light gets slowed down in the medium that it's in. You'll see that this is a ratio of speeds and that this ratio always has to be greater than 1 because light, the fastest it can go is c. So if light is going speed c here, then our ratio equals 1. You got c divided by c. But if light is going any amount slower than c, then this v is slightly less than c, so your denominator is slightly less than your numerator, and you get a number that is greater than 1. This means that if you have a number for your index of refraction for a certain material that is a very big number, then the light travels very slowly in that material. But if you have an index of refraction that's much closer to 1, then you have light traveling very, very quickly in that material. And this equation is, of course, worthy of your bag of tricks. Please open up your textbook to page 490. Here's mine. If you look on page 490, this is page 490, at the bottom of the page, you will see table 1. It says indices of refraction for various substances, and then it has a list of all the different values of N, the index of refraction for different materials like diamond or fluoride or glass or ice. Whoa, an update is available. That is so exciting, but I don't really care right now. So sorry. Or you can see in the bottom the gases at 0 degrees Celsius. You see you have air and carbon dioxide. Hey, go ahead and check out that table. And can you please make note of where does light travel the fastest and where does light travel the slowest? You should see that light travels the fastest in air because air has an index of refraction, NA, I'll call it, which is equal to 1.000293. It travels the slowest out of the options on this table in diamond, where it has an index of refraction of 2.419. You notice two things here. First of all, there are no units on N. That's because you've got meters per second here divided by meters per second here, and so those will cancel out. Second, you notice that the index of refraction for air is much lower than the index of refraction for diamond. That's because in diamond, those molecules are those little carbon atoms are really tightly packed together, and so the light doesn't have much space between the atoms where it can go see. It's spending a lot more time in atoms because atoms are so close together. It's spending a lot less time actually zipping between them. In air, as you know, the molecules are very far spread out. So to go from one atom to another atom, it has a lot of space where it travels C before it interacts with the next molecule. And so this should make some sense to you about why we have a lower index of refraction in air than we do in diamond. You do have to have one index of refraction memorized, and that is the index of refraction in air. But you don't need to have all the decimal points memorized. You only need to know the first 3, like this. So you need to know that the index of refraction in air is equal to 1.000. Hey, sounds a lot like 1, yeah? This shows us that in air, light is going nearly to speed c. It's very close to speed c in air. Okay. And now, to learn about what you really came here to learn about today, which is how to catch a fish with your bare hands. Now, if you wanted to catch a fish with your bare hands, you would look down into the water, and what you would see is actually not going to be totally what reality is. Take a look at a pencil in a cup of water. If you take a look at a pencil in a cup of water, you see that what you're seeing in the water is not really what reality is. You see that the pencil looks way bigger in the water. It actually looks magnified in the water. And additionally, it actually isn't exactly where it is. You can see that it looks slightly off where it's supposed to be. So there are two issues when you're trying to catch a fish with your bare hands. The first issue is that fish, when you're looking at it in the water, is going to look way bigger than the fish actually is. And the second issue is that the fish isn't actually going to be where you think it is. So we're going to talk about what strategies you would need to know based off of Snell's law and the laws of refraction that would allow you to catch a fish with your bare hands. Let's go ahead and draw a picture. The picture that I'm going to draw for you here is going to be what we call a refraction diagram. And you will draw, sorry, I got to erase, go away, bye. You will draw a refraction diagram anytime you do a refraction problem. Here's what it looks like. We're going to start by drawing this whole fishy situation. You start by drawing a nice horizontal line that divides the two mediums. Down here we'll have water, up here we'll have air. You will always label your two mediums. Then after that we're going to draw a nice dotted line between them, or I should say directly perpendicular to the two lines. And it'll look something like this. Here's your nice dotted line, but pretend that's perfectly straight. This dotted line is a line that we call the normal line because it's perpendicular to the line that divides the air and the water. Now please draw your fish. Here is my little fish in the water which I would like to catch. Now if you're looking at a little fish in the water, then your eye is likely somewhere like up, I'll erase that. Your eye is likely somewhere up here-ish, going to travel to your eye. That's the only way that you would ever see it, is if light from the fish went from the fish up toward your eye. But here's the problem. When the light from the fish gets to the boundary between the water and the air, the light from the fish is not going to keep on going in a straight line like this. No, it's going to refract. It's going to bend. Now this is where you should check your refraction rules and see if this makes sense to you. The bottom part of the light ray, and this is like where it would be really nice if you could like hold up a little pen next to this thing, and so it's going to probably be easier on your paper than it is for me. But I'll draw my little pen here. The bottom of the light ray will end up in the water, so it'll end up going slower. The top of the light ray will end up in the air, so it'll end up going faster. So this end is going to go much faster than this end, and this thing is going to end up bending down. And it'll bend somewhat like this. Here are the angles that we measure. We say that this angle, please go away. We say that this angle here is the angle of incidence because it's our incoming angle. We say that this angle right here is our angle of refraction because it's our refracted angle. We always measure both of these angles from the normal line. Something to notice here, you'll see that our angle of incidence is definitely not equal. Whoa, I almost made that into a Q. That was crazy of me. Our angle of incidence is definitely not equal to our angle of refraction. These are not the same. Notice my angle of refraction is much greater here than my angle of incidence. Here's something that's always true. Whenever light goes from a more dense medium to a less dense medium, it will refract away from the normal line. Whenever light goes from a more dense medium to a less dense medium, it will refract away from the normal line. Now, you have two options here. You can either just memorize that rule, or you could just use your pen trick every single time and check and see which way your pen would bend, and if you could use that skill, then you are all totally set to go. So whatever works for you is totally great here. But the angle of refraction is going to be greater than our angle of incidence here because we're going from a more dense medium like water to a less dense medium like air. This means that when your eye looks at the little fish, your eye is going to trace back. Your eye can only see in straight lines. And so your eye is going to trace this back and your brain is going to say, oh, I get it. It looks like this little fish comes from right here. And your brain would also say, oh, it looks like that little fish is much larger than the fish is in real life. So you would see a fish that is enlarged, and you would also see a fish that is up higher in the water than it actually is in real life. This should already give you some clues about how to fish with your bare hands. You should say, okay, Miss Wilson, I know that when I aim, I need to reach down lower in the water than I think. Because the fish isn't as close to the surface as I think it is, it's actually a little bit deeper. And second, it looks magnified to me, so I'm probably thinking that fish is a little bit smaller than I really think that it is. You're probably going to want to take your hands and hold on a little bit tighter to that fish for multiple reasons. First, because it is a little bit smaller than you think it is. But second, because that fish is probably not going to like being caught by your bare hands, and so it's probably going to try to wiggle its way out of your little fingers there. And fish are very slimy, so I'd recommend a nice tight grip there. Now here's the next question. If a fish were trying to catch a human, what tips would you give to that fish? Think about it for a second. And let's draw a picture. Here we go. I'm going to just see if I can undo. Sorry, this will only take like 5 years to hit the undo button a gazillion times. But look, I think it's working. And, okay, well, that's more than I thought. Okay, yep, and okay, bye, okay, and perfect, yay! Now, if the fish is going to look at you, then the light from you has to come down to the fish. So here's what the fish is going to see. The fish is going to see light coming from you, light coming from you down to the water here. But when it gets to the water, the light from you is not going to keep on going in a straight line. No, it's going to bend. And here's where we can use our little rule. The top part of this wavefront is in the air, so it's going to go much faster. The bottom part of this wavefront is in the water, so it's going to go a little bit slower, which means it's going to turn overall this way. And it's going to turn down. Oh, wait, let me erase my little marker here. It's going to turn down and bend towards the normal. Sorry, one more time. I just down towards the normal. Turns out that light going from a less dense material like air to a more dense material like water bends towards the normal line. So here's what we have once again, is we have this angle is now my angle of incidence because that's my incoming angle. This angle is now my angle of refraction because that's my outbound angle. Once again, we see that they are not at all the same angle, they are different angles. But you can see that actually, like, this whole drawing looks exactly the same as my drawing from last time, except that I switched the directions of the arrows, and then I renamed my angles here. Other than that, looks totally the same. This fish is going to think the same way that you think. Its eyes say, I only see in straight lines, and so its brain is going to trace this little light ray back and say, where did it come from? And it'll say, oh, yes, I see. It looks like that human being is up here. Like that. So the fish will see you up a little bit higher than you actually are. What tips will you give to fish? Well, I would tell a fish, hey, when you jump out of the water to catch that human, you should jump a little bit lower than you think you should. You looking at the person, you're going to think that you want to go and overshoot, but actually you want to go down and undershoot. Now, this is something that is very, let's just say that you should be very careful what you do with this information, because as we know that catching a fish with our bare hands is actually, it looks easier for us than it actually is, because it looks like that fish is closer to us, but in reality it's actually further from us. For a fish, it's the opposite. A fish catching a human is actually easier than the fish thinks that it is. The fish thinks it has to jump out of the water this high, but actually the fish only has to jump out of the water this high. So, please be careful with this information. If it looks like the fish just has to jump up here, the fish really only has to jump up here. And so it's much easier for a fish to catch a human than the fish think. Please do not spread this information to any fish of the world, because that would put us in a very dangerous sort of situation. Luckily though, fish don't know rules about refraction, and so we are in great shape so far in terms of our survival from fish capturing. Good news, yeah? Now you say, okay, Miss Olson, that all sounds good and fine, but if I catch a fish with my bare hands, I don't want to just like generally know vaguely that like the fish should be lower than I think it is. You're saying, I want to know real angles, Miss Wilson. Tell me the truth of the matter. Where exactly is that fish? Well, I have an equation that you can use to enhance your psychic abilities so that you will know the exact location of that fish. Let's try it now. That equation is known as Snell's law, and it looks like this. We say that Ni sine of theta I is equal to Nr sine of theta R, where N here is the index of refraction for the incident material. This N is the index of refraction for the refracted material, the material that you're refracting into. This is sine of the incident angle, and this is sine of the refracted angle. Remember that we said that this is not true for refraction. This is what's true for refraction. And this equation is, of course, a psychic enhancing kind of equation, and it is worthy of your psychic bag of tricks. Let's go ahead and try an example problem and see if we can use it. Eraser, go, do your job. Actually, let's make the eraser enormous. Yes, giant eraser. Go, giant eraser, go. Okay, I really could just get a new document here. I am realizing that now. Yes, that would have been much faster and much simpler. But here we go, I've already put in all this effort, and bam, it's all erased. Okay, perfect. Let's try a little practice problem. Hey, this time I'm going to draw it sideways. Let's say that you had a situation where you had some water over here, and you had some air over here. And now we'll make our normal line perpendicular to both surfaces. Hey, can you imagine a situation where you would have like, I don't know, like air on one side and then like water on the other side, like in here, like with a little like horizontal, a little vertical line in between them? Could you think of any examples that might be like that? No, me neither. But let's just make a hypothetical one. Let's say that light rays were going to come from the air into the water. And let's say that they were going to come in, they were going to come in at an angle of 33 degrees. Now this is where I always ask my students first, am I going to label this as theta I or theta R? And they always say theta I, Miss Wilson, because this is the angle of incidence. That is so very true. And then I ask them, which one am I going to label? Am I going to label option A right here as theta I? Or am I going to label option B right here as theta I? And they say, Miss Wilson, we're going to label option angles with respect to the normal. And I say, wow, yes, that's so true. You are so very correct about that. So I'm going to call this angle 33 degrees. Now, here's the question. Which way is it going to bend when it gets into the water? You say I'm going from a less dense material to a more dense material, so I'm going to bend towards the normal line, or you could just do it like by using your little pen trick. And this is the angle. Let's try and find it. This is going to be my angle of refraction here, once again defined from the normal. In order to find this angle of refraction here, you would need to know a little bit something about the indexes of refraction. So one thing you would want to know is you'd want to know that the index of refraction for air is, well, you have it memorized. It's 1.000. You'd also need to know the index of refraction for water, which in this case, I'll let you know what it is. And on a test, I would always tell you the index of refraction for water. It's 1.333. Lovely. Now the question is, what's going to be our angle of refraction here? A few things to notice. First, anytime you do one of these kinds of problems for me, you're always going to draw a nice diagram, a nice refraction diagram. You can label all of your knowns and unknowns on the diagram, which means you have no other place to label your knowns and unknowns. Your labeling is done, and you are ready to get going. Let's start using Snell's law here. We're going to start by rewriting our original equation. And then we'll rearrange our equation to solve for what we're looking for. In this case, we're looking for theta r. So I'm going to rearrange this equation to find theta r. What I'm going to do is I'm going to divide both sides by nr. So I get sine of my angle of refraction is equal to my first index of refraction times sine of theta I divided by my second index of refraction. Then, to get rid of this little sign here, I'm going to take the inverse sign of both sides. I get that theta r is equal to the inverse sign of ni sine of theta I all over nr, like this. And now we're good to plug in numbers and get going. But first, before we do, hey, check your indexes of refraction here. Which one are you going to call nr and which one are you going to call ni? Well, you're saying, Miss Wilson, I know that the index of refraction of air, that's going to be my incident index of refraction. And my index of refraction for water, that's going to be my refracted index of refraction. I say, perfect, okay, I'm glad you know these things, because you got to plug in numbers right now, and if you plug them in wrong, then you'll get something on your calculator that says, error, out of domain, or you're not in the right place, or you really just messed this whole thing up. So make sure that you get those oriented right. We'll say sine to the -1 of, check my index of refraction for my incident material. That's going to be 1.000 times the sine of this angle here, which is going to be 33 degrees, all over nr here, which is going to equal 1.333. Now, we're good to plug it into our calculator. When you plug it into your calculator, you're definitely going to get a number for sure. But the question is, how many sig figs do you want? Here's what I'm saying, is I'm saying 33 has the least number of sig figs here, so I'm going to go with 2. And that gives you an angle of 24 degrees. Box it up and you're good to go. Hey, check it. Look at this diagram. Does it make sense to you that this angle would be 24 degrees? You said, yeah, because it's supposed to be less than 33 degrees. And I get over here that my angle is, in fact, less than 33 degrees. It's 24 degrees. There's a little practice with Snell's law. Now, we've talked about refraction and how it works. We've talked a little bit about Snell's law, which you can use to find all of your different angles. But we got 2 more things to talk about. And the first thing that we're going to talk about today is, it's not the first thing we're talking about today, but the first of the last 2 things that we're going to talk about today is called the critical angle. And I am going to get out a new drawing for this because it's not worth erasing everything. Okay, we're going to start by talking about the critical angle. After we talk about the critical angle, that is going to lead us into a discussion on the indexes of, I was about to say indexes of refraction, total internal refraction, or reflection. But we're going to start with critical angles. Let's go ahead and get started here. Here's the idea of a critical angle. You could imagine that I could get into a situation where I have 2 materials, a denser one like glass, and a less dense one like air. And let's say that I have this normal line between them like this. And now let's say that I have an incoming light ray coming from the glass and it's on its way into the air like this. So I have an incoming light ray this way. Here is my angle of incidence. Now my outbound angle, because I'm going from glass, which is a more dense medium, higher index of refraction, to air, which is a less dense medium, lower index of refraction, then I am going to see a bend away from the normal, something like this. idea, okay? Track and see if you can follow this here. Imagine if I sent in a different angle. Imagine if this time I went in from the glass this way, like this. Well, then you can imagine that my resulting angle, if this was my incident angle, my resulting angle would have to be just a little bit lower here, like this. And so on and so forth. If I sent one a little bit higher up, it would have to be a little bit lower here, because it has to bend a little bit further away from the normal. Well, what if my incident angle was crazy? What if I had an incident angle like this, such that my, oh gosh, I just really don't like the way that I'm drawing these, like this, such that the angle that comes out on the other side, the light ray that comes out on the other side, would never actually make it out of the glass. What if the refracted light ray just, oh gosh, this is so embarrassing, just, okay, well, yeah, okay, yes, it's hard when I do draw straight line the first time, just like this, just went straight along parallel with the surface of the glass and never made it out. We call this angle the angle at which I would have to launch a light ray so that the refracted light ray ends up parallel with the surface of the glass. We call this angle, this is my incident angle, but this angle in particular is my critical angle. Here's the idea. If you launch a light ray at the critical angle, it'll never make it out of the first material. The critical angle only works, by the way, when you're going from a more dense material to a less dense material. You have to go from glass to air. You can't go from air to glass. But if you're going from a more dense material to a less dense material, it's possible to launch light at a critical angle such that it never makes it out of the glass, and the light ray just goes nice and parallel here with your surface. Now, here's what's interesting, is if I were to launch at an angle that was even less than the critical angle like here, or even greater than the critical angle right here, since we're measuring the angle from the normal. If I go at an even bigger angle here, then at that point, this won't refract anymore, it will just reflect back into the glass. The critical angle is the difference between a light ray refracting out of the material and into the new material, or a light ray reflecting back into the old material. If it reflects back into the old material, then it's going to follow the law of reflection, and your angle of incidence here is going to equal your angle of reflection here. Go ahead and take a second and write down in your notes, more specifically with like words and stuff, what is the critical angle? And now, let's go ahead and calculate it. Okay, well, I can't erase it. I should just erase it all. No, at this point I've committed. Okay, we're going to do it. And bye. Okay, great. Now this time, the critical angle really differs based on what materials that you have. Like which materials you're going from and to. Like if I'm going from glass to air, that's a different critical angle than if I'm going from air to glass, and than if I'm going from like water to air, or than if I'm going from like glass to water. I don't know why I keep trying to redraw this line perfectly. It's not going to be perfect. Stop being goofy, Miss Wilson. So let's try to find the critical angle for the specific situation when we have light that is going from water into the air. In this situation, I'm going to send in my light ray at a very specific angle of incidence, which is going to equal my critical angle, which is what I'm looking for. And my resulting light ray is going to go just along the line here. And this is my angle of refraction. Hey, anytime you're at the critical angle, your angle of refraction is 90 degrees. Let's go ahead and see what we can do. Before we can do this problem, you would have to know that the index of refraction for air is specifically equal to 1.000, and you need to know that the index of refraction for water is specifically equal to 1.333, like this. We'll label this one NI because it's my index of refraction on the way in. We'll label this one NR because it's my index of refraction on the way out. And now, here's what we'll do. We'll start with Snell's law. We got Ni sine of theta I equals Nr sine of theta R, like this. And now we're plug in numbers here. We got sine inverse sine of. My index of refraction on the way out is 1.000 because I'm going into the air. Then I do sine of theta on the way out. Hey, sine of theta on the way out, isn't that equal to 90 degrees here? You know that sine of 90 degrees is just equal to 1. Divided by the index of refraction for the incoming material here, and we divide it by 1.333 here. And we are going to get, when we type that into our calculator, a number. Now, before we talk about the number that we're going to talk about, the number that we're going to get, let's talk about sig figs. A lot of students say, oh yeah, we're going to have one sig fig here because we left this at 90, but that's not true. Because when we're looking for the critical angle, we're looking for the angle at which this refracted angle is exactly 90 degrees. And if this is exactly 90 degrees, well then you have infinity sig figs here. So we're going to base our sig figs off of these two numbers here, and so we'll write this as, I do believe it's 48.61 degrees. And there you go. That's your critical angle for going from water into air. Now, it would be completely different if you were going from glass into air, or from water, or from glass into water, or some other material like that. But that is what the angle that you have to send in light at in order to get it to refract perfectly along the surface. Any angle that you send it in at that's greater than 48.61 degrees, and this will just reflect back into the water, like so. Which leads us to our next concept, and our next concept is a concept that we call total internal reflection. Total internal reflection occurs when you launch something into a material at an angle that is greater than the critical angle like this, and that light ray never makes it out of the material, but just stays totally internally reflected inside of the material. Now, I can show you an example of this, but in order to do it, I will have to turn out the lights. And in order to do that, I will have to walk across the room. So, I will be right back. One moment, please. Okay, perfect. Here we are. That made just like a very slight difference, but that's okay. I still think you're going to be able to see it okay. Okay. Here's what I have. I have this giant, like weird plasticky sort of bendy sort of thing. And here I have my laser pointer, which you can't really see it. Like, here, I'll show it to you on my hand. There it is. It's actually, wow, this is crazy. It's actually purple in real life, but you can't even really see it as purple. You can mostly see it as like a whitish kind of color. Wow, wild. Okay, so anyway, here's what we're going to do. And I've never done this like on a camera before, so I don't really know how this is going to work, if I'm totally honest with you, but we're going to go ahead and try. Here I have this little like crazy bendy sort of situation. Here's what I'm going to do is I'm going to take my laser pointer and I'm going to shoot light straight into this little bendy end right here like this. Now when I shoot it straight in, I'm going to shoot it at an angle that is greater than the critical angle. I'm shooting it in at 90 degrees. So when I shoot this thing in here, we're going to get what we call total internal reflection. If you have total internal reflection, then the light will never be able to leave the plastic. Now the question is, where will the light end up? And what you should see is that the light will come out of this end right here, which already looks like really, really bright, even though it's not. Wow, that's so weird. It's probably because I have total internal reflection. Whoa! Wait, sorry, I'm freaking out right now. Hang on. Oh my gosh! Oh wow, this is so cool. Okay. Here's what you're seeing right now. Explain what you're seeing. Hey, do you see how right here, what this little thing is aimed at right now is the light that's coming from like right outside the window over here, basically. So I have white light that's coming in from outside the window. When it comes in right here, it comes in at an angle that is greater than the critical angle, and it follows through the whole tube so that it makes it all the way out. The end of the tube right there and the outside end of the tube looks totally blindingly white. But if I take my thumb and I cover up the end here, then you can see that now you can't see the light from outside the window anymore. Instead, you can see my thumb. Wow, Wow, isn't that great? Well, you can't really see my thumb, but you can see the colors of my thumb right there. Now let's try with my little laser pointer and we'll see how we do. And I can try it. I have a red laser pointer too, so we'll see if we can make it red because this is supposed to look purple, but it kind of looks white to you. Okay, let's see if we can get it here. And, yeah, that doesn't really look super purpley. Like, yeah, a little bit purpley, but not really. Okay, let's try it with my red. 1 second. Luckily, I always keep my laser pointers very close to me. Okay, here we go. Here's my little case for my red laser pointer. We'll take it out here. Okay, now let's see what we can do here. My red laser pointer is a little bit broken and I have to use a pencil to press down the button, but that's okay. It's going to work out fine. Okay, here we go. Let's see if we can use it. Ah, yes, there you go. Wait, am I pressing it down? Is this working? No, it's not really working. Oh gosh, this is embarrassing. One take videos are crazy, but you're along for the ride. Thanks for coming. I'm so glad you're here. It's so fun as we do this together. Okay, I'm going to use my mouth. I'm sorry. I know you're not supposed to do stuff like that. Okay, here we go. Okay, here we go. Oh, gosh. Well, maybe this just isn't worth it. Sorry, this is, like, really chaotic and difficult. The main point is that you're supposed to see that the light stays inside of the little tube the whole time. That's what we call total internal reflection. It also works with things like this. Wait, oh, here we go. Okay, coming back, I swear I'm coming. Okay. Here we go. It also looks like things like this. I don't know if you ever had one of these things when you were a kid, but they are totally awesome. Look at it. You turn it on and it's so sparkly and fun. All that it is basically a flashlight connected to these little cords at the end. And the light shows up on the very ends of the strings. And I always thought that was the coolest thing as a kid. Like, how does the light get from there and only show up in the ends? Like, that made no sense to me. Well, here's the truth is that you've got a total internal reflection sort of situation. So what happens is the light travels through each of these little nylon strings. It gets totally internal reflected here because it's coming in at an angle that's greater than the critical angle, and so it never leaves these little things. It can never bend outside. It just keeps getting reflected back and forth and back and forth and back and forth along the whole length of the tube. And so you can see at the end there, each of these little dots here at the end is filled with the light that it had at the beginning. Even if I bend it, it still makes it through the end because of total internal reflection. Isn't that so nice? That's the idea of total internal reflection. And that, ladies and gentlemen, is pretty much it. That's pretty much the gist. We talked about today, we talked about refraction and how refraction happens with light. We talked about how light even refracts at all. Like, how does that even happen? We also talked about how a fish will look lower down in the water, and it'll look higher up in the water, so you have to reach lower down. It also looks bigger. It looks magnified in the water. We also talked about how you can use Snell's law to calculate what the exact angles are. We talked about what the critical angle is. It's that angle at which if you launch light that way, it's never actually going to make it out of the medium, which leads us to this concept of total internal reflection, which is when the light never makes it out of the medium and just bounces back and forth within the medium itself, never making it out, never escaping. And that, ladies and gentlemen, is a little bit on Snell's law and reflection. I hope you have a great, wonderful rest of your day. Thanks for bearing with me when my demos don't really work on a virtual format. So good to see you all in a virtual format, and I hope you have a great rest of your day. Bye, good people. And this is the part where I have to figure out how to end it. Okay, we can do it. And stop the video. Wait, oh gosh, right here. Okay, bye. Bye for reals.